Hi everyone, I'm Tashi. I'm supervised by Peter, and I'm going to be talking about interactive generative models for music. I thought this slide was quite good. It came up automatically when I put the title in. PowerPoint generated this for me in an interactive way. So what is a generative model for music? Well, it's kind of trying to learn the process of how music is generated rather than trying to learn the actual data of the music itself. This is kind of the state of the art of what's possible. So this is from a video by 2 Minute Papers, if you want to watch the rest of it, explain how the model works. But basically, it is working on the audio waveform directly. So this is the same format that CDs are made in. And this involves thousands and thousands of samples every single second. So we have a huge model to try and model this. And so it takes about a couple of hours to generate just a 2-minute song. So that's not really very interactive. You can't say, oh, I like this bit, but I want to change this, because it would just take too long and you'd give up. So moving on to the interactive side, this is something called Doodle, which was one of people's doodles 2 years ago, where you could put in these black notes at the top and it would automatically find a harmonization for you in the style of a bar chorale. This is really cool, but not that useful. How many people actually want to write bar chorales these days? And it's not really very interactive. You just have the notes to pick, and then there's no other way you can change it. So this is kind of a development of that, where you can, instead of just putting in the top line, you can add in the alto, tenor, bass lines as well. You can choose what key you would like it to be in, and the temperature is kind of how similar to Bach in style is it, or kind of how different. They developed this further in a project called Cococo, where again you're inputting the melody line, but this time you can kind of choose which parts you want to generate rather than generating one of them. You have these sliders in the top right, where you can kind of say how similar or different is this to existing Bach chorales. You can choose the major and the minor key. And it also gives you a list of options when you click generate, and you can choose between these options and get it to generate more options that are similar to these options or different. So what is my project about? It's about how can we make this interactive even better. Previous user studies showed that this kind of interaction gives humans more kind of ownership over the music that's being generated. It feels like they're making the music rather than the computer. So in the Bach Doodle, we had scores, which is what's traditionally used by musicians to write down music. It's very difficult for non-musicians to understand what's going on. And then in the Bach chorales, we had MIDI piano rolls, which is what computers use. Again, this is quite hard for humans to read, although it's more precise. But what about being able to draw music? So we can abstract away from these sophisticated notations and just give the computer a general idea of the shape of the music we want to make, and let the AI kind of decide the precise note values and positions for us. Why would we want to do this? Well, perhaps in an educational setting, people getting first exposed to music creation. When I was at primary school, in computer labs, I used a program called Dance EJ, where you would drag and drop clips of music and make your own song. This was great, but we could make it more interactive and more engaging if you could change these clips, perhaps by drawing over them. It might be useful for music professionals who want to critically iterate different kinds of music. And it might even be useful in a music therapy kind of session. A lot of people struggle to express themselves and find that music is a very good way to do this. And combining this with an artistic aspect may help. So what did I do? There were 3 parts to this project: a music model, a curve model, and a web interface. I'll go through these one by one. So for the music model, I took lots of training data from the International Piano E competition, where they put optical sensors inside this grand piano so they can record which keys are being played and how hard the hammers are hitting the strings. And this gets turned into this piano roll representation that we've seen before, which is great. But how do we turn this into a script so we can use machine learning on it? Well, like Philip was saying, we need to put this into a vector form. One way of doing this is to have different kinds of events. So we'll have an event if a note starts, an event if a note ends, an event if the volume of the note changes, and an event for how long it's been since the last event. And we kind of stick all of these together into one single vector. So onto the model, I use a variational autoencoder, which has 3 parts. An encoder network, which is typically a neural network. For images, this is usually a convolutional neural network. And for sequence data like text and music, and LSTM is commonly used, although more recently transformers are being used here. We then have a latent space, which represents the parameters of Gaussian distributions. And this kind of stores the structure of the music that we've passed through the encoder. We then have a decoder, which is essentially a mirror of the encoder, and it changes this latent space representation back into the original input sequence. So to train this network, we use something called the elbow, the evidence lower bound, which we want to maximize. This has 2 parts. There's a reconstruction loss, which is how similar the output vector is to the input vector. We want these to be the same, so it's reconstructed by the network. And we also have a KL divergence, which constrains the latent space, so it's similar to a Gaussian distribution with zero mean and unit variance, so that when we go to make new latent vectors, they're going to be similar to latent vectors we've seen before. This is useful, as you can see on the left. We have 2 columns here. The one with lots of dots moving around is what happens if we just put random vectors next to each other. And the one on the right is when we take random parameters from the latent space distribution and pass this through the decoder. We get something that's a lot more coherent. The next model was to kind of turn this music into shapes, into drawings. So I came up with these 10 curve classes. In the bottom left, you can see something similar to the piano roll representations we had before, except the velocity information and the note length is excluded. In this kind of classical piano music, there's lots of notes happening at once. So I used a moving average to kind of make sure there's only one note at a time, and to keep the kind of overall direction that the music's going in. And then I'm just using a mean squared error loss to compare these dots to one of the classes and see which class fits the curve the best. We also have a web interface to bring these 2 elements together. So someone can draw in a box on a sketch pad the shape of the curve that they want the music to sound like. This is then matched to one of the classes. And then music is generated in the style of that class using a conditional VAE. And we end up with a piano roll, which you can use to play back the music that's generated. So how did it go? Unfortunately, it sounds a bit like a cat playing the piano at the moment. When training, it's able to accurately reconstruct the input vectors, and looking at how the latent examples are drawn from the distribution, it does look like a distribution with zero mean and unit variance. But when we actually look at the generative music at the top there, you can see what the training data looks like. There's lots of structure, lots of repeating patterns. And at the bottom, it's kind of a lot more random. There's definitely a lack of pulse and a lack of it's kind of quite discordant music. For the curve model, this worked quite well. This is the distribution across the different kinds of class. So how many of the training examples were found to be in each class. When trying to condition on these curve classes, however, the examples really didn't change shape that much. Maybe 1 or 2 of the notes in the sequence were changed, but not the whole shape. And this is the third part, which is a website you can visit, and you can draw a line and press the generate button. And at the moment, it generates Twinkle Twinkle Little Star because I haven't connected it to the back end with machine learning models. So what's next? First of all is to try and simplify the model to make sure that the conditional VAE is actually working. So I chose 10 classes, which is similar to the MES dataset with handwritten digits from 0 to 9. And that can correctly condition, so you can ask it to generate a handwritten digit of 1, for example, and it will be able to do so. But maybe conditioning with just 2 examples may be better. We could also be doing interaction studies to verify how well these models are working, both rating how musically good they are and how well the curves match, how well the person's intention when drawing the curve matches the music that's actually generated, as well as taking a step back a bit and asking kind of what curves would people actually want to draw if they're asked to do this kind of thing. And then perhaps basing the curve classes around this. For the music model, I think this can be improved by augmenting the data set. So transposing all of the music we have into the 12 different keys, and also changing the timing information, so the piece is effectively being played slightly faster or slightly slower. And hopefully this will fill up more of the latent space. I think what's happening presently is it's learning only part of the latent space, and then there's lots of the latent space that's empty, that's not being used by the model. And then when we're generating random samples, it's generating these spaces and the decoder doesn't know what to do with them. Another option would be to change data sets to use much simpler information than piano information, just a single line melody. I haven't done this because it would take quite a long time to trawl through all the different MIDI databases and make sure that the data is consistent. With the curve model, we could perhaps use feature detection with CNNs and clustering. So instead of setting out with classes ahead of time, we're kind of finding common patterns in what people are drawing. For example, how many times it goes up and down, or the overall direction of it. And then, of course, the interface needs to be connected with the back-end models. That's everything from me. We finished quite early. Wow. Thank you.
Questions? Alex?
That's really cool. I'm curious, when you move from the bug representation of music to the curve, do you do anything to consider when you move from 2 notes to 1 note, the harmony of the 2 notes represented? Say if you're a major and minor third, you take the average of the 2, you get a second. Which doesn't sound anywhere near as nice.
So the question was, am I taking into account harmony when I'm taking averages over these curves? Not so much, it's just to take the overall direction of the music. So say the music goes up in this section, it doesn't really matter how much by it goes up. There are lots of different ways it can go up, and hopefully the model will recognize all of these ways, and it will just pick one when it's being generated based on all of the surrounding notes. Does that answer your question?
Can I just follow up on that? So could you bring up that slide with, where you sort of talked about that one? So I guess you're referring to that process. So what struck me now is that, of course, doing the moving average is just one way of aggregating these points. But you know, there could be two motions that are sort of, one is going up and the other one is going down, and if you average them, then it's remaining constant. Right? So what occurred to me is that maybe there you want some kind of mixture model there. So those notes on the left could be a mixture of two movements. That's not easy to detect, but then you also have occlusion, of course. But I guess that would go a little bit in your direction, that it doesn't try to make one curve of the whole thing. And that may also explain with your conditioning, that sort of it kind of all evens out a bit. It doesn't really much.
Yeah, so the point was music can move in multiple directions at once, especially with piano music, you've got two hands. And even going back to the previous point as well, a melody can go down, but the harmony can actually be rising, depending on the chords that are being played. Even though they're played further down the keyboard, there's a sense of them going up because of how they relate to each other. So this isn't really covered by the current moving average, but as Peter points out, maybe a mixture model would better reflect this, so we're kind of capturing multiple motions at the same time.
Thank you for improving that.
So you should, I've seen these sort of curves all the times and so on, and you're sort of struggling. I think you were sort of trying to work out how to express, how to classify the curves was one of the sort of problems that you were studying, so wasn't it? So I suppose my question is, how well do you think these sort of 10 curve classes do? Do you think you managed to cover all of the curves possibly goes well? Or?
My hunch is that no, this is not a very representative sample, which is one reason why I'm suggesting user studies to kind of get what people would draw. But the possible number of curves is basically innumerable. There are so many ways you can go up and down. I calculated these by just dividing the x-axis into 3 spaces, so it can go up, up, down. And these are the 8 possible plus 2 extras, which I added just up, down, and down, up. But if you wanted to divide this into like 10 sections on the x-axis to get more information, that's several thousands of possible combinations, and that just makes the vector basically too long.
Yeah, so my question is on the limitation for training data because of the copyright issue. So for this generative model, you need a lot of data. So I think, do you have any solution for this? Because I mean, I don't have a solution for this in mind. But do you think limitation of accessing training data would be a major issue for what the kind of stuff that you're doing?
So the question was about copyright of music and being able to use it as training data. Copyright doesn't actually cover using machine learning for music, using music for machine learning. It doesn't go against, it doesn't prevent composers from making profits on their own music. But the trouble is, how do you get hold of all of the music for free? You still have to buy it. So even though it's not breaking copyright to make music, it's still very difficult to get hold of that much music.
So do you think companies like Spotify, that they have access to all the music, are they allowed to use their data to train such a model?
Yeah, Spotify does do lots of machine learning on the music they have.
There are lots of interesting questions in this space. For example, it reminds me of what's going on now with training models on GitHub code. I forget what the name is of the system. And so that code has all sorts of licenses, you know, like code is in the public domain, and the question is, what does Microsoft, so what are they allowed? Are they allowed to turn that even into a product, right? A trained model that's trained on public source, you know, open source code? What's the status of the model? I feel it's probably related to some code law.
Exactly.
We need, obviously, we need Andrew also. Yeah, great. Anybody else?
I got a really good question. If we go forward, I think 3 slides. Oh no, just 2 slides. The top and the bottom image of the piano sheet stuff.
Yeah,
they're different timescales on the x-axis.
Yes, they are different timescales.
Okay.
I think the top one is longer extract, and also different pitch scales. You can see that the key is close together on the bottom, but it's just to give you a general idea of the patterns that aren't being replicated yet.
I thought that was the case, but I thought maybe the system had learned to press the piano keys for like 10 times as long.